Now let's take a look at the last example of this lecture. We want to model a system that is very famous and it's called Newton's law of cooling. So let's just consider an example where Newton's law of cooling might be used. Let's say that I want to bring soft drinks in the class and drink it, but I want to drink it cold because that's why it's called cold drinks, right? So I want to keep it cold, and that's why I brought the drink in a cooler. So I'm expecting that the cooler will keep the cold drink cold and I will be able to drink it cold. So what happens is that in reality, even though the insulation of the cooler keeps the heat from the environment away quite successfully, it doesn't keep all of the heat away because there is no perfect insulator and heat eventually does seep in. So slowly but surely the drink gets warmer. So let's say small t is time and the temperature of the drink, let's say that is theta d, theta d. So this will be drink's temperature. And let's say theta E is the temperature of the environment, temp of environment. So the rate of change of theta d dot, the rate of change of theta d, this is dependent on itself and the temperature of the environment, because we understand that if theta d is very low, it will change a lot in a very small time. If theta E is very high, then theta D will also change a lot in a very small time. If they are actually quite close to each other, then the rate of change won't be as high. So what we can think is that the rate of change of theta D is a function of theta D and theta E. So let's say that this rate of change only depends on the difference between theta D and theta E. Is it a valid argument? Let's examine. Just think that if a drink is at 0 degrees Celsius and the environment is at 10 degrees Celsius, will the drink get warmer faster, or will it get warmer faster if the drink is at 0 degrees Celsius but the environment is at 30 degrees Celsius? We can already understand that the situation where the environment is at 30 degrees Celsius, in that situation the drink will get warmer faster. Now let's take a look at, will the drink get warmer faster if it is at 0 degrees Celsius and the environment is 30 degrees Celsius, or will it get warmer faster if it is at 10 degrees Celsius and the temperature difference is at 40 degrees Celsius? Which case will get the drink warmer a bit faster? Actually, both cases, the drink will slowly increase in temperature, but the rate of change will be the same, because the difference between the temperatures is the same. So we can understand that this value theta dot of D is actually dependent on the distance between these two values. So now, as we are considering the law of cooling, where a cool thing is getting warmer, let's say theta E is actually larger. The environment is actually at a higher temperature than the drink itself. So for argument's sake, we write theta E minus theta D. So the difference becomes positive. And we say that theta dot depends on the distance. So let's say this is a function of the difference between theta E and theta D. Now, if theta E and theta D is equal, we can expect no change, because as they are at the same temperature, the drink will not get warm, and nor will the environment get any colder. So there is no rate of change of theta D, as theta D is now constant. As theta D won't change, it is constant, then the differentiation of theta D will be 0. So we can expect that if these two are equal, then theta E minus theta D equal to 0. So if this is 0, that means that f of 0 is 0, because in this case it means two things. In this case, it means that the difference of these two temperatures is 0, and it also means that from a conceptual point of view, it also means that this is also equal to 0. So this part becomes f of a, f of 0, and this part makes it f of 0 equal to 0. Now we will use Taylor expansion to find an approximate representation of this function, because we understand that this function is a function of the difference between these two things, but we do not know any actual representation of this function, so that we can carry out the separation of variables technique and solve it. We do not know any kind of actual representation of this function. We just know this. What I am trying to say is that we know that a function is dependent on x, so we only know f of x. We do not know whether it is x square plus 1 or whether it is root over x minus 101. So we need to understand what the representation of this function might be. Up to now we only know this, but we do not know what the f of x might look like. So as we have no idea how it might look like, we have a general way of proceeding from here. We can simply use Taylor expansion to find an approximate representation of this function that will really closely approximate the function. Maybe it's not exactly close. If we go up to the infinite term of the Taylor expansion, then we will get the exact representation, but we can't do that. So we will just be happy with an approximate representation. So what is the Taylor expansion? We first have to understand what Taylor expansion is to use it. Here I will just write f of 0 is 0. This is what we found from our conceptual argument. So Taylor expansion states that if the function let's say f of x, if f of x can be differentiated at n plus 1 points of an interval. Okay, let's say there is an interval. The number line extends here and here. There is an interval, and the function f of x can be differentiated at n plus 1 points. N plus 1 points in this interval. And this interval also contains a point named x naught. These are the three requirements. There has to be a defined interval. On that interval, there has to be n plus 1 points at which f of x can be differentiated at, and one of those points must be x naught. What is x naught? X naught is a value for which we know the value of the function, and in that case x naught is 0. So if we have all of these conditions met, then we can write the function f of x to be approximately equal to f of x naught plus f prime of x naught times x minus x naught divided by 1 factorial. Then the next term will be f double prime x naught times x minus x naught whole square divided by 2 factorial. And this will go on and on until we reach the nth term, fn at x naught times x minus x naught to the power n divided by n factorial. This is the approximate representation that we get from Taylor expansion. So let's use the Taylor expansion in our case. In our case, our variable is this. So in our case, f of theta e minus theta d, this function can be approximated using this. This is our x naught. So f of 0, I will just write approximately equal to f of 0 plus the differentiation of f at 0 times this thing minus 0, because x minus x naught is 0, so this thing over 1 factorial and on and on. Now if we consider that theta e and theta d and theta e are actually quite close to each other, then the difference between these two, the value or the result of this subtraction will be really small. So as we are raising the exponent of that subtraction one by one in each term, this whole value becomes smaller and smaller until it becomes totally irrelevant. And if it is lower than 1, then just on the next term, when we are squaring it, its value will be so small that all of these will be irrelevant. So what we are doing here is we are only taking the first two terms of the Taylor expansion and ignoring all of the rest. So now let's use the known value of f of 0 that we already know. F of 0 is 0. So this thing is 0. 0 plus, oh my mistake, this should be approximately equal to. If this is 0, then 0 plus this is a constant because we have put a value of x into the function that we get after differentiating it once. So as we have put a constant value in place of x, that function has now become a constant. It's like this. Let's say f prime of 0 is x squared plus 1. F prime of x, let's say f prime of x is x squared plus 1. Let's just say, for example, if we put 0 in place of x, then f prime of 0 becomes 1. So what I am trying to say that as long as it is described by x, it is an algebraic expression. But when we put in a constant in place of x, we calculate and then we can reduce it to a single constant. So this is a constant now. So let's say this constant is k, and this is our variable theta e minus theta t, and 1 factorial is just 1. So what happens is that we have approximately, I won't be continuing to write approximately now, because now that we are taking this to be true, we can just say that this is equal to the right answer. So we approximate the function to be of an expression like this. So as the function has this expression, if we put the value of this in this equation, then we get theta t dot is equal to k times theta e minus theta t. So now you again see that this equation is of the form of our original most important differential equation. Why? Because the temperature of the environment will always remain constant, because the environment is so vast and expansive that when a body of any mass interacts with it in a manner of exchanging heat energy, the mass of temperature always is so much larger than the mass of the body that we are talking about, that the temperature of the environment actually never changes. It is like taking some water off the sea and expecting the sea level to decrease. How much water do you want to take from the sea? 1,000 liters, or let's say 10,000 liters, or let's say the amount needed to run a whole country. Do you think even after taking all of that water off the sea will make the sea level go down? It won't, because the sea is so expansive in comparison to the land area of a single country that no matter how much water you take from the sea level never goes down. That's what I am trying to explain. When a matter is interacting with the environment and trying to exchange temperature with it, only the temperature of that matter changes. The temperature of the environment actually never changes, because the mass of the environment is so much larger than the mass of the matter itself. So we can consider the mass of the temperature of the environment to be a constant. And we have discussed previously that in the case of differentiating and integrating, basically in the case of calculus, what actually matters to us is the shape of the graph, and not where the graph starts or how much it rises or anything like that. We are concerned with whether a graph is exponential or not. If a graph is like this, it is exponential. There can be a constant that makes the graph rise faster. There may be a constant that makes the graph rise slower. But the fact that this graph rises in an exponential way, this is what we are interested in. So our main variable is this, and this is like this is a constant minus our main variable. So basically this equation is basically of the form of y dot is equal to constant times y dot is something times our variable. This is what this equation is conceptually similar. So we can say that maybe we don't yet know how to solve it, but we can say from our conceptual understanding that even though we don't know the solution, we know that somehow the solution will be an exponential solution. So this is called Newton's law of cooling. This law was described by Newton himself, and there is a limitation to Newton's law of cooling, and that limitation maybe some of you have forgotten about it and some of you remember. That limitation is that the difference between these two temperatures have to be small. Why? Because if this temperature difference is large, then subsequent terms of the Taylor expansion will make it larger and larger and larger. So the Taylor expansion won't be a converging function. It won't become asymptotic to some particular line. The Taylor expansion will be a divergent function. So we won't be able to get an approximate representation of this function, because this function will keep going away and away from us. So it will only work when the temperature difference is very small. And from a mathematical point of view, we can argue that this will only work when it is smaller than 1, because anything greater than 1, if we raise its power, eventually it will become larger and larger. Even if it is 1.99 zeros, then 1. If we square it, this becomes larger. If we square it, this becomes larger. And larger and larger and larger and larger until the amount that is increasing in every step becomes relevant. So let's recap. First we took a look at a very important differential equation. Then we took a look at some other famous equations. Then we learned how to solve a differential equation for the first time. Then we used that technique to solve our famous differential equation. We used that technique to solve some other equations. We learned about loss solutions, and finally we learned how to model very simple systems using differential equations, and then we solved them to visualize how those systems behave. So along with this lecture, there are some problems set in the lecture content. Please go to the website that was mentioned in the first lecture. You can find the directions of finding that website and downloading the materials in the part 2 of the first lecture. Go watch it if you haven't already, and download the materials from MIT OpenCourseWare and solve the problems associated with lecture 2. It will be good practice, and if you actually don't solve by yourself, then it will not be of enough use to you. You have to get your own feel for it. So go through that, solve those problems, and we will discuss it in the third lecture. Thank you.